This video provides an introduction to passive bandpass filters. It corresponds to the first part of section 11.7 of the Applied Analog Electronics textbook. Now, the goal of a bandpass filter is to let through a particular range of frequencies, the passband, and to attenuate frequencies outside that range. So if we look at the thing from the standpoint of a Bode plot, we're expecting to see a gain that looks something like this. So this is the magnitude of the gain on a log scale, and this is frequency, again, on a log scale. And at one corner frequency here and another corner frequency here, between them we're going to have a almost constant gain. Outside that, it's going to fall off until it gets to be zero at DC or infinity. Okay, so how do we do this with a simple passive filter? Well, we can do it with a resistor and a capacitor in series and another resistor and capacitor in parallel. So the input here goes through RU and CU, and the output is connected to VREF through CD and RD. Let's look at what this thing does just sort of intuitively before we try and do the math for it. If we're looking at DC, what's going to happen? Well, both the capacitors at DC are going to behave like open circuits. There's an insulator in the middle. So there's no connection to the input, and we've just got a resistor that's not connected to anything and a resistor to VREF. So the output is just going to be connected to VREF. That means there's no variation as a result of the input. The gain is zero. That's what we want. What happens as we go to infinity? Then both the capacitors become short circuits, and we have the input directly connected to the output. Doesn't look so great, but oh, the output is short-circuited to VREF. So the output is just going to be whatever VREF is. There may be some current flow or something, but output is just VREF. Again, doesn't depend on the input, so gain is zero. And so at the extremes, this thing does what we want it to do. I haven't shown you that it's got a roughly flat spot in the middle here. We'll worry about that in a little while. What is the gain of this circuit? Well, it's just a voltage divider. We've got an input, we've got DC rail here, and we've got output between the two, the impedance on either side. So V out over V in is just whatever the impedance of this series pair is, parallel pair, and divided by the sum of the two impedances, the parallel pair and the series pair. Okay, that's just voltage divider equation. Now we need to figure out what are those impedances. And at this point the math starts getting a little bit uglier, but still doable. So let's look at ZU first. That's just RU plus 1 over J omega CU. And because I know it's going to help later on, I'm going to get that in the form of a fraction rather than as a sum. So just 1 plus J omega RU CU over J omega CU. And if we look at the other impedance, where we have the two things in parallel, that's RU in parallel with 1 over, RD in parallel with 1 over J omega CD, or 1 over RD plus J omega CD. And again, things might get a little simpler if I can make this just be a fraction, so multiply time divided by RD to get RD over 1 plus J omega CD RD. Okay, and now I've got to plug that ZU and that ZD into the gain equation for the voltage divider. And I will start over on a new sheet of paper to do that because it gets a little bit big. V out over V in is ZD over ZD plus ZU, and ZD was 1 over RD plus J, sorry, I already simplified this, RD over 1 plus J omega RD CD over, and then this one on the bottom here was RD over 1 plus J omega RD CD plus, now I have ZU, which was 1 plus J omega RU CU over J omega CU. More simplification needed. Let's multiply top and bottom by the 1 plus J omega RD CD, and also top and bottom by J omega CU. So I get J omega RD CU divided by J omega RD CU plus 1 plus J omega RU CU times 1 plus J omega RD CD. That looks like quite a messy formula. But we can check to see whether or not it has the right behavior as we get to the extremes. What happens if omega goes to 0? Well, everything here is going to be going to 0 except for this 1 times 1 here. So if we look at that just sort of asymptotically, this is 1 plus a bunch of things that are going to 0. So as omega goes to 0, the gain goes to J omega RD CU. All right, that's the sort of behavior we want here, and that tells us kind of what this line here is doing. That line is omega RD CU. All right, what happens as omega goes to infinity? Well, all these things go to infinity, but the J omega squared goes to infinity much faster than anything else on the bottom. So we can sort of ignore everything except for the J omega RU CU times J omega RD CD. And then if we take top and bottom and simplify things, we get G goes to 1 over J omega, and what's left on the bottom is going to be RU CD. And that's what's telling us what this line is doing. That line is going to be approximately omega RU CD. So we have these two asymptotic lines here. All we really need to know is what's happening here in the middle. What's the peak value? And I'm not going to do that by hand. I do have in the book how I can do the calculations. Basically taking the magnitude of this thing, and then taking its derivative to find out where the derivative is 0, doing that with Wolfram alpha because it's way too messy to do by hand. And it comes out to be a very simple answer. So I'm just going to give you that answer, and that is the peak occurs when omega is equal to 1 over the square root of RU, CU, RD, CD. So basically just take your two time constants, take their geometric mean, that is multiply them together and take the square root. 1 over that is omega. And that is the omega for the peak of the curve here. Well, if you look for where the corner frequency is, you can just say, well, what is the gain at this peak? And again, the math gets kind of messy. I put it in the book. But we can get, I'll just give you the results here. Look in the book for the derivation because it's not worth the time on the video to go through it all. But the gain at the peak is going to be RDCU over RDCU plus RUCU plus RDCD. Okay, and then what you can do is you can look for where does that value equal omega RDCU. Sorry, this one is 1 over on this side. Or where does it equal 1 over omega RUCD? And again, I'm not going to do that algebra here, but the corner frequencies come out being that omega is 1 over RDCU plus RUCU plus RDCD. Or the other corner is at 1 over RUCD plus 1 over RDCD plus 1 over RUCU. And it's possibly instructive if you want some algebra practice to actually get these values from knowing what omega is and having what the asymptotic line approximations here are, but it's not worth taking the time in this video to go through them. These are not things that you need to memorize, but it's something, and certainly not something you need to be able to derive in a hurry, but it's something you should look up when you need them, is what is the gain of passive RC filters. Later on, we'll be looking at a different type of bandpass filter, an active bandpass filter that includes an amplifier, and those are actually a good deal more versatile. And so we won't be using the passive filters like this very often once we've gotten to the point of being able to do the active ones. The active ones are actually easier to design than the passive ones, but sometimes you can't afford to stick in an extra amplifier in a circuit. They take up space, they take up power, and you can get away with doing this simple passive design. So what I recommend doing is looking in the book at how the derivation is done, but don't try to work out all the details unless you really enjoy doing algebra.